Hey guys, it's Andre from High Performance Academy. Welcome along to this week's webinar. Now, we're going to be talking today about what on face value might seem like a pretty dry topic. We're going to be talking about pull-up resistors. You'll find out what they are and you'll find out why they're important. Now, it might be a dry topic, but if you don't understand how a pull-up resistor works or why you may need one, you're going to have the potential for a lot of trouble when you're setting up an aftermarket ECU. Before we get into that though, just wanted to talk about a few things that have been going on around here over the last week. And we're going to actually start by just covering off an Instagram I put up late last week. If I can get my words out properly. This is one that we took when we were over at Goodwood Festival of Speed, or some photos that we took when we were at Goodwood Festival of Speed. So we'll head across to my laptop screen for a moment. And if you aren't already following our Instagram account, please make sure you do so. We do post really regularly, and well, at least we think we post up some pretty interesting content. There's always some pretty good discussion in there as well. So this is a Mercedes 190 E Dtm Race Car. So this is from back in the early 90s, and I don't know, I think this is probably maybe a slightly more pure era for race cars in general. We saw the DTM cars. Also, the mid-90s, probably one of my favorite eras for British touring cars, super tourers, etc. Just a lot of really cool race cars were built over that period. But the important thing, or why I kind of like this period, is that they were a little bit rawer than what we see now. Not so many driver aids, a bit more driver skill perhaps required. Anyway, that's not really the purpose of the discussion. So the car here, what I found interesting was the way they had a 2.5 litre base engine, and I think at the end of their development they ended up around about 375 horsepower. Depending who you talk to or where you look, those numbers seem to vary from about 350 to 375. I like to be a little bit generous here, so we went with a larger number. Now, a couple of things that it's obviously difficult without the aid of a turbo to make those sorts of numbers from a four-cylinder engine with just 2.5 litres, and there's a couple of things that they did to try and help. First of all, you can see here in this shot that I've just drawn all over poorly, they used, instead of a conventional set of individual throttle bodies or a single plenum and a single throttle, they used a slide throttle arrangement. Now, nothing particularly unusual about that. There's a variety of different techniques when it comes to getting air into the engine or throttling the airflow into the engine. Our conventional throttle body that we see in most of our factory road cars and most people use in race applications is fine, it works well, but what it does do is, even at wide open throttle, there is still something stuck in the airflow there that can disrupt and reduce the airflow. So the slide throttle body, when it is completely open, offers absolutely no restriction to airflow. But a few questions about whether the slide throttle does impact on the airflow, causing turbulence, etc. at part throttle. And this is something I don't have any data on. I could imagine that that may be an issue, but these engines really, they are focusing more on the outright top-end performance at wide open throttle probably than the drivability. Now, another thing we can see on this shot, it is a little bit tricky, but if we follow the fuel lines, we can actually see there are two sets of injectors fitted here. So we've got a primary set, which are the ones on the left-hand side there, right up by the intake port at the head flange. Pretty conventional location for our port fuel injectors. And then we've got a secondary set that go into the carbon inlet runners that are pre the slide throttle bodies. And this isn't done because they couldn't support the fuel requirements with a single set of injectors. Obviously, our fuel injector selection has grown dramatically over the last few decades, but we could still get injectors that were big enough back in this era for 350 plus horsepower. However, what they were doing was actually using staged injection here, and the idea is to stage in those secondaries pre-throttle body at wide open throttle and higher RPM, and the aim was to try and get a more homogeneous fuel air mixture, basically trying to get every last scrap of power out of the available air that was entering the cylinders. And probably my favorite part that came out of this interview or this tech tour was the fact that the engineers actually fitted or retrofitted variable cam control to these engines. So in particular here you can see the little cylinder on the front of the intake cam there. So this wasn't a continuously variable cam control system like we see now. This was a switched cam control system, still popular on a range of different engines. Particular one that jumps to mind is Nissan used it on the SR20 as well as the RB series of engines. So it allows the cam to be advanced at low RPM to help low RPM performance, and then retarded again at a certain point in the rev range in order to optimize high RPM performance. And that was important as well because these engines did rev through to 10,500 RPM. So trying to get as wide a torque curve as possible was pretty important. So there's a little bit of insight into that car. I probably should actually show you a picture of what the car looked like. Interesting point that came out of talking to the Mercedes engineers there. They actually had just come recently from a Mercedes historic event in which Lewis Hamilton was attending, and Lewis actually got to cut some laps in this 190E. Obviously a little slower and a little less powerful than what Lewis Hamilton's normally used to. Apparently after about 3 or 4 laps they were struggling to get him out of the car, and he was grinning from ear to ear. So just to show you that you don't need all the power in the world, and you don't need to be driving an F1 car to have a lot of fun out on a racetrack. Right, now we have been talking a little bit recently about our black Toyota 86, the one we've got our 450 horsepower V8 in it, and we've been battling with this car with a few issues around cooling in particular. So we have made some changes, and for those who have been watching us religiously for a fair while, you probably remember a few months I talked about the fact that we made some changes to the cooling system in terms of originally there was a large oil cooler fitted directly in front of the radiator. We also had an over the radiator cold air intake designed for a Holden Commodore that was fitted. This came down over the top of the radiator, again blocking some of the flow. So we made some changes there, moved the oil cooler so it wasn't in front of the radiator, put a conventional air filter on it, so freed everything up there, and we were hoping that this was going to keep our engine cool. In the one race that we did prior to making these changes, we were really battling and having to short shift the engine because after about 5 laps it was getting up to about 110 degrees C, and obviously at that sort of temperature not really going to help with the life expectancy of the engine. Now the reason that we've had a few delays here is that in the meantime we have also been making a lot of other changes to the car. In particular, we made some changes with the gearbox, fitting a sequential 6-speed gearbox into it. We've also had problems with the temperature control in the rear differential, so we fitted a larger Cusco billet aluminium rear housing for that. And we've talked about this in one of our pre-shows prior. One of the things that was brought up is that on its own wasn't going to fix the cooling problem, which we pretty much knew already. However, it does make it easy for us to fit an external oil cooler, given that we are planning to use this car for some endurance circuit racing. So we got the car to the track on the weekend, and I just wanted to take you through some of the data. So we'll head across to my laptop screen for a moment. So this is from one of the faster laps that got done while we were out there. We're only putting in sort of 3 to 5 laps at a time, so definitely not really punishing the car like it would be in endurance racing. But what we're looking at here on the Motec data, obviously at the top in red we've got our engine RPM, we've got our throttle position and our throttle pedal position, given that this is drive-by-wire, but we'll come back and talk about that in a second. We've got our intake air temperature, which as we can see through this particular lap is staying relatively under control, around about 17 degrees C. We've got our oil pressure. Obviously we always want to be keeping an eye on that to make sure that's under control. And then at the bottom here we've got our engine oil temperature and our engine coolant temperature. So bearing in mind that this is only one lap, it's hard to draw too many conclusions. If we use the minimum and maximum function on the Motec i2 software, we can see that in blue our engine coolant temperature minimum was 81 degrees and a maximum of 86 degrees on that lap. Now that's a much bigger improvement compared to where we were north of 100 degrees C. Bearing in mind again only a few laps in there. What we can see as well though, our oil temperature minimum of 99 and a maximum of 104. Now, those temperatures on their own aren't really anything to be concerned about. Definitely, I've got no issue running our oil temperature up at 104, and generally I like to be somewhere around about 100 to 110 degrees C. It actually can be some problems if you run your oil temperature too low. But when we're only looking at a snapshot of data like this, it's hard to get a really good idea of what is going on and what may go on if we continue to go and put in another 10 laps after this. So if we just zoom back out, so we're having a look at a wider section of the data here. In fact, we've got all of our data here from when the car went out on the track to the point where I got out of the throttle because I was coming back in for a cool down lap. So if we look at the left hand side at the start of the data here, just after we get out on track, we can see our oil temperature sitting at 69 degrees, our coolant temperature 82. And what we can see with our coolant temperature is essentially it cycles up and down a little bit. We've got a maximum of 89, a minimum of 81, but the important thing is we've got this gentle oscillation depending on whether the car is under sustained wide open throttle operation or whether it's going through a corner at lower RPM or braking. So that's good. This is what we want to see. We've got this gentle oscillation and we're never really seeing a continual trend with our temperature climbing. Unfortunately, the same can't be said for our oil temperature here. And when we initially get out on the track, we see the oil temperature drop a little down to 65 degrees C as we start getting airflow over the cooler. However, from this point on, it's a constant rise. And basically at the point where we get out of the throttle on our cool down lap, we're up to 105 degrees. So it doesn't take a rocket scientist to kind of extrapolate that trend that, whoa, not with that one, that trend that we've got going on there, and we've got this constant sort of movement of our oil temperature up and to the right. So what this indicates to us is probably we're going to have issues for endurance racing and we are going to be fitting a larger oil cooler. It's not all bad though. Getting control of our engine coolant temperature is a massive win, so we're pretty happy with that. Now at the same time, if we head across to have a look at some of our other data here. If we go to our transmission general, we've got our temperature for our gearbox, so that's in the center here in purple, and we've got our temperature for our differential in green at the bottom. Now this is definitely not good news. We can see we've got that really sharp increase at the start of the session. Transmission temperature 79, diff temperature 79 basically, and by the end of that session here we have peaked 105 in the gearbox, 123 in the diff. Now, the gearbox manufacturer has recommended the grade of oil that we're running in this transmission and also suggested we don't go over 110. Obviously, for reliability purposes, we're going to take their advice. So we are in the process of fitting oil coolers to both the diff and the gearbox. So I'll just take you through and show you what that all looks like. Bear with me for a second here. Right, so on my laptop screen at the moment, this is the front right-hand corner of the car. It's a little bit hard to really make out what we've got going on here. This is actually the brake cooling duct that normally connects up to the front bar. So what we've got is a Mocal diff oil pump here that's been fitted up in the chassis. And it's a little bit tricky here trying to choose a location for one of these oil pumps because obviously we've got a chassis that is pretty tight for room. We also don't want to put this in a place where it's overly exposed to being damaged in a crash. So Brandon spent a fair bit of time looking at our options. We basically came to the conclusion that if we end up in a crash that's bad enough to damage the gearbox oil pump mounted here, we're probably not going to be continuing anyway, so gearbox oil temperature is the least of our issues. So Brandon has also mounted a little filter element in here. So this is quite a coarse filter element. The aim is really if we have a gearbox failure and we get a dog tooth or something snap off, we want to prevent that going through the pump and damaging the pump. So it's not really there so much for fine debris. Then we have the cooler core itself. So that's just mounted to the side of the radiator, so it's going to get airflow straight from that front bumper. Looking at the side of our TTi 6-speed gearbox, the gearbox is made with cooling in mind, given that these are used quite commonly here in New Zealand in endurance racing. So the centre CNC machined alloy plate there has a fitting for both the oil drain as well as the oil return. So those are just hooked up to our pump there. At the rear of the car, this is the Cusco diff cover that we talked about a while back, and we've just fitted, or Brandon has just fitted connected to -6 AM fittings there and run the plumbing to the rear of the car. And again, we're trying to choose a location where this little cooler core is not going to be exposed to unnecessary damage. And again, while it's a little bit hard to see, this is the main chassis rail here, so that actually extends back behind the oil cooler. So again, it's going to be a pretty serious shunt if we're in a situation where that oil cooler is damaged. And while you can't see it in these photos I've got here, the pump has been mounted up inside the rear of the car. So the aim with this is that both of those pumps will be controlled with an output from our Motec C125 dash. If we had fitted a power distribution module, we would actually do it direct from the power distribution module, and this means that we can have them turned off when the oil temperature is low. Once it gets up to maybe 90 or 100 degrees, then we can switch those oil coolers on, and if we've got excess cooling capacity with those, then the pumps will cycle on and off. We will be going to a power distribution module in this car for these functions in the not too distant future. That way the dash can still control the operation of them using a CAN message sent straight out to the power distribution module. Simplifies the wiring because we don't need to wire an auxiliary output from the dash up to the power distribution module in order to switch them. But another nice feature with the power distribution module, and I quite often get asked, why would we spend, or why should you spend the money on a power distribution module? Where are the advantages? Because they are still more expensive than relays and fuses, but the ability to data log a lot of information from them can be just one of their advantages. So where I'm going to with this is that we can data log the current draw from each of the pumps. Now what we're going to see in particular is that if there was a blockage, some debris ended up blocking one of those filters, it's going to be much harder for the pump to move the oil, so we're going to end up seeing the current draw increase. Likewise, if there did end up with a failure of one of the fittings, the line came off, because the pump's now going to be sucking air, the current draw will go down. So by data logging that, looking at peak values, and we're going to be also sending this information via telemetry, someone who knows what they're looking at can look at this data and diagnose that there's been a failure or a problem before it actually causes any significant issues to the car. Right, so hopefully we'll have all of that gear set up pretty shortly, and we're going to be heading back to the track in the not too distant future to check it out and make sure that that all works exactly how we'd expect. Now at the same time, again, for those who have been following us, I talked briefly just then about the TTi 6-speed sequential gearbox. One of the reasons we were at the track was to test the effectiveness of that gearbox, make sure that everything was working. We are using a Motorsport Systems strain gauge gear knob, and that gives input to the ECU so we can perform clutchless upshifts and downshifts. So I just want to show you a little bit of data on what this actually looks like here. So again, if we jump across to my laptop screen, we're looking at the transmission page here, and I've just set up, I actually don't have all of the data, which would have been nice to show you here. We're still in the process of setting everything up. I've just set up a shift page here, worksheet to go through what we need to look at. We've got our RPM at the top here. We've got the gear, that's the next channel below, and this is the one that we're sort of interested in here, which is our gear lever force. So this is the output from the strain gauge gear lever that's converted into newtons of force. So we can see, for example, the little spike here, this is the driver pulling back on the gear lever for an upshift. So the driver can stay at wide open throttle, in particular here, if I just zoom in a little bit, so you can see that this area here highlighted. In the bottom we've got our throttle position. This was a full throttle shift from third into fourth gear. So the ECU takes that signal in, performs a ignition cut which allows the dogs to disengage, and then the next gear can be selected. Now the interesting thing, or what I wanted to show you though, is the downshift. So here we've got a section where we are downshifting, so you can see that the voltage or the Newton force into the strain gauge goes the opposite way as you'd expect. So the ECU in this case is going from fourth down to third gear, and we can see that we've got our two traces at the bottom here. The orange trace is the driver's throttle pedal, so we can see that the whole way through this downshift area the throttle pedal is completely on the floor, that's at 0%, and when the ECU detects that downshift request, what it does is it automatically blips the throttle at the actual engine. So that's what you can see there, the discrepancy between, whoops, not that one, the discrepancy between the driver's foot pedal position and these two blips that are being performed on the downshift. So what that does, the idea there is to match the revs for the next lowest gear, and if you get everything right, it is a really smooth, seamless shift. Now the Motec SE also makes this a little bit easier because it knows what the RPM will be for the next gear, knows what the gear ratios are, so it's pretty easy to calculate for a given engine RPM. If we downshift into a lower gear ratio, what the RPM for the engine should be. So what it can do is it instigates a downshift throttle, a downshift engine RPM limit. So if you're a little bit over enthusiastic with the blip, it will actually hit that limit. It's not something we want to be doing because when it hits that limit, it will bring in a RPM limit cut. So you actually end up with quite a sharp crack sound, which is a little bit off-putting on the downshift. So that's just part and parcel of tuning that closed loop gear shift control. Now, while we were playing around at the track, we actually narrowly escaped a pretty serious problem. So again, we'll jump over to my laptop screen. Brandon noticed this as soon as we got the car back up on the lift once we came back from the track. And as you can see, the rear CV here, the cap screws that hold the CV, the two-piece CV together, have all backed out. Now, I actually put these together myself, so I know full well that these were tight, and this seems to be a potential issue with a few cars that run at our local track, Highlands Motorsport Park. Another team that we deal with had exactly the same thing happen with their Volkswagen Golf TCR race car, and while we're only kind of guessing here, it seems like it could be down to where the cars with a reasonable amount of power go over the bridge overpass at Highlands Motorsport Park. They will actually get light. They basically can end up off the ground if you're going just the right speed, and this can allow obviously the rear wheels to unload, so you end up sort of touching the rev limiter and they grab back down. Anyway, we know they were tight, so we're not really going to trust that Loctite's going to fix that. So the solution here, which is what Brandon's been working on this morning, is a new set of bolts here, and this time they have been lock wired or safety wired, so this means there is absolutely no chance of those cap screws working loose. So this is the fun, I guess, when it comes to modifying cars, is you fix one problem and you find another. So your job is really never done, and there's always little areas that you find that do need work and do need some improvement. Now, speaking of improvement, I also wanted to just mention why I've got this suspension set up on the table in front of me at the moment, and we'll just jump again across to my laptop screen. So for those who haven't been following or keeping up with the play, this is our one of our Toyota 86 development cars, and we are launching another brand, which is RaceCraft, as you can probably tell by the graphics wrap on that car. So RaceCraft is going to basically be a sister company to High Performance Academy. All of our existing High Performance Academy VIP members are also going to get free access to all of our RaceCraft courses, and RaceCraft is working basically in the online education around driver education as well as race car setup and maintenance. We're really excited about this project because we think there is just as big a lack of knowledge in this area as there is in the tuning, engine building and wiring industry. We've got our first course just about complete now, which is a DIY wheel alignment course, so you'll learn how wheel alignment works and how to actually check and make your own wheel alignment adjustments. And we're just in the process of filming a worked example, which will be the case of fitting these components we've got here into our RaceCraft Toyota 86. So I just want to mention what we've got here. So we've got a set of MCA Red Series coilovers which will be going into the car. MCA in particular, they've got a couple of series of coilovers. These ones are designed really more around race car use, so not suitable, not really designed for on-road performance. They're a little bit stiffer, a little bit more spring rate in them, which is better for our track use. In particular, we've got for our front struts here, these are a McPherson strut with the Toyota 86, so it uses a camber adjustable strut top to make it really easy to adjust the camber. One of the problems with the ZN6 Toyota 86 chassis is that there really is in stock form almost no adjustability to get our alignment geometry where we want it. Another aspect checked with the coilovers from MCA. I'll just try and show these under the overhead camera. I'll just drop into that. So we've got the camber adjustable strut tops, but they also removed the factory eccentric or the common eccentric style camber adjuster, which are so easy to end up having move. And instead, MCA used these offset washers, and the center of these washers is offset to allow you to get your camber wherever you want it. As you can see though, they are then bolted to the strut body, so there's absolutely no chance of those moving once you've got your camber where you want it to be. So along the lines of trying to get a little bit more adjustability into the chassis, we are also fitting some parts from SPL Parts in the US. So in particular here, we've got one of their rear lower control arms. So this is adjustable, so we basically make this lower control arm shorter or longer, which influences the track width, but also the camber at the rear of the car. And these use a spherical bearing instead of the factory rubber bush. And the reason that that's important is that factory rubber bushes or aftermarket urethane bushes, they will tend to flex under the high loads we see on a racetrack. And what this means is that the alignment, the toe settings and the camber settings that we get when we're setting our car up, they're not going to necessarily be exactly what we end up with on the track when we're hard under braking or cornering really hard. So spherical bearings on the outside will not move around. On the downside, they will transfer a lot more noise, vibration and harshness into the chassis. So not necessarily ideal for a street car, but for a no holds barred race car where performance comes first, these are the way to go. Another problem with the spherical bearing I will mention as well is that they do tend to wear quite quickly. At the front of the car, we are also using some more parts from SPL Parts. So this is their lower control arm. Well, it's missing a part at the moment, but hopefully you'll be able to get the gist. So again, this provides adjustability for track width. With the other arm that is missing from this as well, we can move the lower ball joint forward or rearward in the chassis to affect the caster. Then we've got another couple of arms here for the rear of the car. We've got an adjustable tow control arm and an adjustable trailing arm or traction control arm, as SPL Parts call them. So pretty excited to get all of those parts bolted into the car really shortly, and hopefully within the next few weeks we'll have all of that edited and that course will be available. So of course, if you are interested, watch this space and we will be announcing more once we have that up and running. Alright, fairly long-winded introduction today, however bear with me because I've just got a couple more bits that I want to touch on. One of those is that we have just released our latest video today. So for those of you who are not currently subscribed to our YouTube channel, make sure you do so. You'll get notified of all of our latest releases. So this is another tech tour that we shot while we were over at Goodwood Festival of Speed. And this is a car that I'm sure a few of you will have probably already watched, or probably more specifically listened to. There's heaps of YouTube clips of this car competing in the European Hill Climb Championship. It is, of course, George Place's old BMW E36. Nothing particularly special about the chassis. It's really the engine that is the exciting part of this car. So it's powered by a Judd 560 horsepower V8 that revs to 11,000 RPM, running through a sequential gearbox. And this thing sounds really just like an F1 car. It is one of the most amazing sounding hill climb cars. I love turbocharged engines, but it is hard to go past a high revving V8 or V10 for that matter. Really, there isn't too much that sounds quite as good. So if you are interested in learning a little bit more about what makes that car tick, head over to our YouTube after this webinar and you can check out that full length video. Lastly, we are running another one of our giveaways. So this time we have got a set of pistons from Diamond Pistons to give away. So I've got one of their examples here, which is for a LS engine, but they are providing any of their shelf stock pistons. So head across to Diamond's website and you can check out the full list of their shelf stock pistons. If you are currently building a project car, maybe you're at the point where you consider considering a engine build, then this might be the perfect time to grab yourself a free set of pistons. Now, you can get yourself into the draw by following the link that the team can now drop into the comments there. Click through that, you can get your name into the draw, no cost to get involved, and you're also going to be able to get yourself some additional entries. There's a few little jobs that you can do, a few little tasks that you can tick off. Each one of those additional tasks will get you an extra entry into the draw. Now, not only are you going to get the set of diamond pistons, you're also going to get our suite of engine building courses so that you're going to know what to do when those pistons arrive. So if you're interested in that deal, jump in there, get in the draw, and we'll wish you all of the best of luck. All right, thanks for watching there. Give me a few moments and we'll just get set up and started into our webinar. Cheers.